Europa and Enceladus are not just icy moons orbiting distant giants. They are prime candidates in the search for extraterrestrial life within our solar system. While Mars has long captured humanity's imagination, these moons of Jupiter and Saturn, respectively, have stolen the scientific spotlight. Their secrets lie beneath their icy crusts, where vast oceans of liquid water might harbour the building blocks of life. Water is the essential ingredient for life as we know it, and Europa and Enceladus have it in abundance. Europa's icy shell, approximately 10 to 15 miles thick, covers an ocean that could be up to 100 miles deep, more than twice the volume of all Earth's oceans combined. Enceladus, though smaller, astonished scientists when the Cassini spacecraft discovered geysers spewing water vapor and organic molecules from its south pole. Beneath Enceladus' crust lies a global ocean kept warm by tidal heating, a gravitational tug-of-war with Saturn that generates internal heat, preventing the water from freezing entirely. What makes these moons so compelling is not just the presence of water, but also the evidence of energy sources and chemical ingredients necessary for life. On Earth, hydrothermal vents at the bottom of our oceans teem with life despite the absence of sunlight. The same could be true beneath Europa and Enceladus's icy crusts, where hydrothermal activity may exist, providing the energy to sustain microbial ecosystems. Enceladus geysers have offered tantalizing hints of what might lie beneath. Cassini's instruments detected molecular hydrogen, a potential energy source for microbes, along with carbon dioxide and organic compounds, the chemical precursors to life. These findings strongly suggest that Enceladus's subsurface ocean could have conditions similar to those found around Earth's hydrothermal vents. Europa, on the other hand, has shown signs of water plumes erupting from its surface, captured by the Hubble Space Telescope and later confirmed by the Galileo spacecraft. These plumes might offer a direct pathway to sample its ocean without having to drill through miles of ice, making it an attractive target for future missions. Additionally, Europa's surface features, chaotic terrains and ridges, suggest active geological processes that could cycle nutrients and chemicals between the ice and the ocean below. While the potential for life is exciting, exploring these distant worlds is no small feat. Both moons lie hundreds of millions of miles away, requiring years of travel to reach them. The extreme cold, averaging minus 260 degrees Fahrenheit on Europa and minus 330 degrees Fahrenheit on Enceladus, poses significant engineering challenges for spacecraft and instruments. Moreover, the thick ice crusts mean that directly accessing the subsurface oceans would require advanced drilling technologies or novel approaches like melting probes. Radiation is another hurdle, particularly for Europa, which orbits within Jupiter's intense radiation belt. Any mission to Europa must be equipped with heavy shielding to protect sensitive electronics. Despite these challenges, scientists are undeterred, driven by the tantalizing possibility that these moons could harbor life. NASA's Europa Clipper, set to launch in 2024, is designed to study Europa in unprecedented detail. The spacecraft will conduct dozens of flybys using sophisticated instruments to analyze the moon's surface composition, measure its magnetic field to confirm the depth and salinity of the ocean, and search for water plumes. By studying these plumes, scientists hope to detect organic molecules or other biosignatures, chemical signs of life. Similarly, the European Space Agency's JUICE, Jupiter Icy Moons Explorer mission, will focus on Europa, Ganymede, and Callisto. While its primary target is Ganymede, JUICE will make several flybys of Europa, complementing the data gathered by Europa Clipper. For Enceladus, NASA's proposed Enceladus Orbilander aims to both orbit and land on the Moon. By flying through its geysers and collecting samples, the mission seeks to analyze the composition of the water vapor, ice particles, and organic compounds. A lander could provide the first direct analysis of surface material, offering a more detailed picture of the Moon's habitability. If life exists on Europa or Enceladus, it's unlikely to resemble the complex organisms we see on Earth. Instead, scientists anticipate finding microbial life forms similar to those thriving in Earth's extreme environments. In the deep oceans, far from sunlight, organisms rely on chemosynthesis, using chemicals like hydrogen sulfide or methane for energy rather than photosynthesis. Both moons have conditions that could support such ecosystems. Enceladus's molecular hydrogen is a potential energy source for microbes, while Europa's ocean, in contact with a rocky seafloor, might allow similar chemical reactions to occur. The presence of salts and minerals in both moons' oceans suggests that they are chemically rich, increasing the likelihood of life. The search for life on Europa and Enceladus isn't just about finding microbes, it's about answering one of humanity's most profound questions. Are we alone in the universe? Discovering even the simplest life forms on these moons would have staggering implications. It would suggest that life is not a rare cosmic accident, but a natural consequence of the right conditions. This realization would reshape our understanding of biology, evolution, and the potential for life elsewhere in the cosmos. Moreover, studying these moons could provide insights into the origins of life on Earth. By comparing extraterrestrial ecosystems to our own, scientists might unravel the conditions that sparked life on our planet. This knowledge could also inform the search for habitable exoplanets beyond our solar system. The exploration of Europa and Enceladus represents the cutting edge of astrobiology, but it also has broader implications for science and technology. Developing the tools to study these moons drives innovation in robotics, autonomous systems, and cryogenic engineering. These advancements have applications beyond space exploration, from improving medical technologies to advancing renewable energy systems. Additionally, the search for life unites humanity in a shared quest for knowledge. Missions to Europa and Enceladus are collaborative efforts involving scientists, engineers, and agencies worldwide. This spirit of cooperation demonstrates how space exploration can transcend national boundaries and inspire global progress. While current missions are focused on studying the habitability of these moons, the ultimate goal is to directly detect life. Future missions might deploy advanced landers equipped with drills, spectrometers, and even miniaturized laboratories to search for microbial life beneath the ice. Technologies like autonomous submarines or cryobots, robotic probes designed to melt through ice, could one day explore the oceans of Europa and Enceladus firsthand. The journey will be long and challenging, but the rewards could be transformative. Discovering life beyond Earth would mark a turning point in human history, opening a new chapter in our understanding of the universe and our place within it. Europa and Enceladus are not just icy moons. They are cosmic time capsules, preserving clues about the potential for life in our solar system. As we continue to explore these alien worlds, we edge closer to uncovering one of the greatest mysteries of all time. The question isn't just whether life exists elsewhere, but how close we are to finding it. And with each mission, each discovery, we take one step closer to that monumental answer.